Hi, I'm Greg Gay with Chalmers and the University of Gothenburg. This is my first talk of the day. By the third, you will probably be sick of me, but in any case, this is our entry in the challenge track, where a set of case examples are presented and researchers apply recent work to those. In this case, I've applied our recent work in what we call adaptive fitness function selection to the Gson serialization and deserialization library from Google. Now, search-based test generation essentially follows a formula. In search-based generation, testers seek input that attains their testing goal, whether that's code coverage, detection of seeded faults, or any number of other possibilities. An optimization algorithm systematically samples the space of possible test input in search of a solution to that goal, guided by feedback from one or more fitness functions, scoring functions that judge the optimality of the chosen input. During this search, the fitness function embodies the high-level goals of the tester. Feedback from fitness functions will shape the resulting test suite, and we choose fitness functions based on their suitability for the goals that we are interested in. For example, a common goal is to attain branch coverage, to ensure that all outcomes of our control divergent statements have been executed. Search-based test generation generally attains that goal using a fitness function based on the branch distance, a nice fine-grained measurement of how close we came to covering each branch outcome. If our goal is branch coverage, well, we know how to attain it through search-based generation. However, for other goals, we may not be so fortunate. Many goals do not have an effective fitness function formulation. For example, what if our goal is exception discovery? Well, we cannot know ahead of time all the possible exceptions a class can throw. Further, while we can do things like count exceptions and try to optimize that count, the results of test generation are poor because that simple count doesn't give us the fine-grained feedback the algorithm needs. Now, another similar type of goal is what we call test suite diversity. When we're testing, it's generally impossible to try every single input. It follows then that different test cases are more effective than similar ones. Try a bunch of things, you'll get better results. That intuition has led to effective automated test case generation, prioritization, and reduction. And while numerous diversity metrics exist, for example, the Levenshtein distance, some of these metrics can serve as poor fitness functions as they also don't offer sufficient actionable feedback to optimize. Now, that does not mean that test suite diversity cannot be attained. Rather, we simply don't know what fitness functions would be effective. There's many different fitness functions out there used in search-based generation for attainment of other goals. Well, careful selection of one or more of those functions, potentially paired with a diversity metric, could provide that missing feedback we're looking for. In fact, we may even attain higher diversity by reevaluating our choice of fitness functions over time based on the changing test suite population. So careful selection and reevaluation of fitness functions could result in test suites that are more diverse than those generated targeting a single diversity metric alone or a naively chosen set of fitness functions. Identifying this set of fitness functions is a secondary search problem, one that could be tackled as an additional hyper-heuristic step within the normal test generation process using reinforcement learning. We call this process adaptive fitness function selection. So adjusting the set of fitness functions can be considered as an instance of the n-armed bandit problem. Given a measurement of diversity, every action we take, every choice of fitness functions has an expected reward, an expected increase in diversity when it's selected. You can see this modified test generation process here. At a defined interval, the reinforcement learning agent will reevaluate the set of fitness functions and refine its estimation of their ability to increase diversity. Because the population of test suites at round n depends on the population from round n-1, reinforcement learning can not only choose effective fitness functions, but it can strategically adjust that choice based on the test suite state. Adaptive fitness function selection has been implemented within the EvoSuite test generation framework. We've added two reinforcement learning algorithms, upper confidence bound, which is a classic reinforcement learning approach that works well for many problems, and differential semi-gradient SARSA, or DSG SARSA, which is an approximate approach adapted for problems with large state spaces, for instance, test case generation. We call this overall framework EvoSuiteFIT. So we've implemented a fitness function to measure test suite diversity based on the Levenshtein distance. The Levenshtein distance is the minimal cost of the sum of individual operations, the insertions, deletions, and substitutions needed to convert one string into another, or in this case, one test case into another. To calculate the diversity of a test suite, we calculate the sum of the Levenshtein distance between each pair of test cases, and then we normalize that score between 0 and 1. Every 5 generations, EvoSuiteFIT will step in and will make a selection of 1 to 4 fitness functions from a set including that diversity score, an account of exceptions, branch coverage, direct branch coverage, method coverage, top-level no exception method coverage, output coverage, and weak mutation coverage. To constrain the number of combinations we can choose from, then we only use combinations that include that diversity score, and we remove a further small number of semi-overlapping combinations like branch and direct branch aren't used together. So ultimately, the reinforcement learning agent can choose between 44 combinations of fitness functions to try and apply to the test suite for the next 5 rounds, after which point it will try and make a decision again. To seed reward estimates, we start by making sure we try all actions in random order, and then we kick in the reinforcement learning process, either UCB or DSG SARSA. After selecting fitness functions, EvoSuiteFIT will proceed through the normal population evolution mechanisms, and after 5 generations have passed, the reformulated population is used to calculate a reward or change in diversity, and will update the expectation on reward afterward. This gives sufficient evolution time to judge the effect of changing fitness functions. Over time, the combination that gains the highest reward will be more likely to be selected again until we finally reach convergence. So we've assessed EvoSuiteFIT for improvement in test suite diversity using 18 real faults from the Gson project to address 2 research questions. First, is EvoSuiteFIT, is this reinforcement learning process able to yield more diverse test suites than static fitness function choices? And second, does increased test suite diversity in turn lead to a greater likelihood of fault detection? So Gson is an open source library for serializing and deserializing JSON input, and it is an essential tool of Java and Android development. A set of 18 real-world faults from Gson are available in the Defects4J fault database, and for each fault, Defects4J provides access to the faulty and fixed version of the code, developer-written test cases that expose each fault, and a list of classes and lines of code modified to fix the fault. We target the classes affected by the faults for test case generation. Our previous work has found this framework as a challenging target for test generation, and we evaluate EvoSuiteFIT in these examples in terms of the attained test suite diversity and fault detection, comparing against 2 static baselines. So to investigate our research questions, we perform the following experiment. Right? First, we take these 18 faults from the Gson project and we target the affected classes of each fault for test generation. We generate test suites. For each class, we generate 10 test suites per approach. We've generated test suites using both reinforcement learning approaches, UCB and DSG SARSA. In addition, we generate tests for 2 baseline approaches representing current practice. The first is the diversity score alone. This will be your likely starting point for a tester who are interested in improving test suite diversity. The second is a combination of the 8 fitness functions that are used in this study. This represents a best guess at what would produce effective test suites, and would be considered a reasonable approach in the absence of a known informative fitness function. We generate using a search budget of 10 minutes per test suite. Afterwards, we remove any non-compiling or flaky test cases. On average, this is less than 1% of tests for each test suite. And finally, we assess our results by measuring the diversity of each test suite using the fitness score from that diversity score function, a score between 0 and 1, where lower scores are better. And we also look at the likelihood of fault detection, the proportion of failings test suites to the number generated for each fault and approach. So here we can see plots of the diversity scores for each technique, the combination of all 8 fitness functions, and diversity alone. And again, because we minimize fitness, lower scores indicate higher levels of diversity. Now we can clearly see here that the diversity score is a difficult fitness function to optimize on its own. When it's the sole target of test generation, the diversity score gives the worst results. There's also a wider variance distance between that first and third quartile in the results. So diversity alone does not offer actionable feedback to the test generation algorithm. Second, we look at the combination of all 8 fitness functions. Now this attains more stable results with a better median. It is a better approach than diversity alone. It offers additional feedback. Right? By adding these additional fitness functions, we give the test generation framework detailed feedback leading to improvements in the final score. Now, however, both reinforcement learning approaches outperform the static approaches. DSG SARSA attains a 62% median improvement over diversity only and a 24% improvement over the combination. UCB is even better with a 75% median improvement over diversity only and 49% improvement over the combination. UCB also attains a 33% median improvement over DSG SARSA. So both reinforcement learning approaches demonstrate lower variance in the results they attain as well. They attain more stable results than either static approach. Using the Varga-Delaney A measure, we can confirm that both reinforcement learning approaches outperform the static baselines with a large effect size, and that UCB outperforms SARSA with a small effect size. Both EvoSuiteFIT techniques, both adaptive fitness function approaches, particularly UCB, increase test suite diversity over the static fitness function choices with significance. Now, there is limited evidence we can use to assess the impact of diversity on the likelihood of fault detection. Only 4 faults are detected by any of the approaches: faults 4, 9, 12, and 17. Now, in past research, we identified several factors impacting fault detection in Gson, including faults that are easier to expose through system-level testing than unit testing, which is what we're performing here, complex data types, and faults exposed through stronger test requirements. So increased diversity alone in the input space really may not overcome the broader issues that are preventing fault detection. However, we do make a couple of observations that suggest potential positive improvement from increased diversity. Right, so examining fault detection across these 4 faults, what we see is that first, all approaches outperform diversity alone. And second, the approach with the greatest diversity, UCB, also attains the highest likelihood of fault detection. In addition, fault 17 is only detected by DSG SARSA, none of the other 3 approaches. That fault is based around serialization of date values, so increased diversity could lead to a wider range of attempted input and method calls. So adaptive fitness function selection could improve the likelihood of fault detection by increasing diversity. However, we really do not have much evidence to go off of here. More examples are going to be needed to draw any sort of clear conclusions on the impact of diversity. So what we do here is we find that adaptive fitness function selection creates test suites that are more diverse than those created using static fitness functions. While the results in fault detection are inconclusive, we do observe that increased diversity may lead to small improvements in the likelihood of fault detection. However, additional research is needed to tackle this particular challenge. Future work on adaptive fitness function selection is going to extend the study beyond Gson to a far greater pool of faults in the defects4j database, and we'll examine other goals that can be optimized in a similar manner. Now, this is a short talk, so I could not get too far into the technical details. So if you're interested, I would like to mention that we also have a full paper on using adaptive fitness function selection to optimize exception discovery that was published at the International Conference in Software Testing this year. The paper is out there. I'll be giving a talk later this month. I would suggest you give that paper a read as well as our challenge track entry. Now, please let us know if you have any questions either now or through email. Thank you.